The next two sections of the chapter, section 3.3 and 3.4, have to do with calculating and using solution concentrations. So as a quick review, a solution is a mixture. It is specifically a homogeneous mixture. If you put something in water and it does not dissolve, then you do not have a solution. You have a mixture or a slurry or something else. The component of the mixture that is present in the greatest amount is called the solvent, and then any other thing that's in there would be called the solute. There could be a solution with several solutes dissolved in the solvent. A lot of the solutions we are going to be working with are aqueous solutions, and for that one, water would be the solvent, and it could have one or several solutes dissolved in it. And then the concentration is a relationship between the amount of mixture you have, the amount of solution, and the amount of one of the solutes that is in it. The first way that we are going to focus on for expressing concentration expresses the amount of solute in moles and the amount of solution in liters. So it's moles per liter. You can write it as moles per liter, either with the whole word, mole, or mole abbreviated, or a capital M. Just remember that this capital M means moles per liter. It does not mean mole. Some people get a little bit confused. You see that capital M and you know it's moles per liter. So let's try this first problem where we calculate the molarity. The concentration in molarity would be the moles of solute over the liters of solution. We are told the volume of solution in milliliters. A lot of times that happens. Milliliters is a much more convenient volume to work with in lab. We seldom have multiple liters of our solution. And so being able to quickly convert between milliliters and liters is a really good skill to have. So we have 0.1000 liters of solution, 0.087 moles. So we can express this as 0.87 moles per liter of sodium hydroxide, or we can use that capital M and say that it is 0.87 molar sodium hydroxide solution. This next problem, again, is calculating the molarity. So we need the moles of potassium hydroxide over the liters of solution. We are told the grams of potassium hydroxide, so we need to convert this to moles. We can either convert it to moles ahead of time, or we could just do it in the process of figuring out the concentration. So we can just take the amount of solute, the amount of KOH solute we have, and the amount of solution. Let's start there. We have 3.27 grams of KOH, and we have 200.0 milliliters of solution. Let's convert the grams of potassium hydroxide to moles, and then let's convert the milliliters of solution into liters. So when we do this, our grams of KOH cancel, our milliliters of solution cancel, and we end up with 0.291 moles of potassium hydroxide per liter, which we can also write as 0.291 molar potassium hydroxide. This next problem gives us the molarity concentration. And so what that means is that we are given the relationship between the moles of solute, the moles of HCl, and the volume of solution, the liters of solution. So this 2.8 capital M means that there are 2.8 moles of hydrochloric acid in every 1 liter of our hydrochloric acid solution. We're going to use that relationship to convert the moles needed into the volume that's needed. So when we multiply this 0.97 moles of HCl by the conversion factor with moles in the bottom to cancel the moles, we end up with 0.35 liters of HCl solution needed. If you want to express this in milliliters, it would be 350 milliliters of the solution. I didn't really specify in the problem, I just asked for the volume. So either one of these would work. All right, here we have another problem that gives us a concentration. And usually when we're given a concentration, we can be pretty sure we're going to be using that concentration to do a conversion because it's a relationship. It's a relationship between the 2.75 moles of potassium hydroxide that are in every 1 liter of our potassium hydroxide solution. We don't have a liter of the solution, we have 345.0 milliliters. So in order to be able to use this molarity as a conversion, we should first get this in liters. Now at this point we have liters of potassium hydroxide. Then we can convert this to moles of potassium hydroxide and we get 0.949 moles of potassium hydroxide that is dissolved in there. Okay, so looking at this next problem, I went ahead and wrote the concentration as a relationship because we're probably going to have to use it that way. And then I also noticed that we are talking about grams of sodium chloride, and so I wrote the molar mass of sodium chloride as well. So these are our relationships. The actual amount that we are trying to convert is the 50.0 milliliters. So this is the amount of solution we have, and we are trying to convert that amount into the amount of solute in grams. Our concentration is moles per liter, so we should convert this to liters first. Then we can use the molarity concentration to convert the liters into moles of sodium chloride. And then we can use the molar mass to convert to grams of sodium chloride. And we do that and find that 9.93 grams of sodium chloride is what we have in that 50 milliliters of solution. So for this next problem, I also am given the molarity. So I'm going to write that as a relationship. And then since we're dealing with grams again, it's very likely we're going to need the molar mass as well. Then the amount that we actually have that we're trying to convert is this 5.5 grams of copper 2 sulfate. We are converting this grams into the volume of solution needed. So first let's use the molar mass to convert the grams of copper 2 sulfate into moles of copper 2 sulfate. And then we can use the molarity concentration to cancel the moles and end up with liters of solution. And we end up with 0.040 liters of solution, and we would probably be thinking about this as 40 milliliters of solution. I included the decimal because we know 2 significant digits, 40 decimal milliliters of copper 2 sulfate solution. Sometimes we get a solution not by dissolving something new, but by diluting something to change the concentration of a solution we already have. So I have rearranged this equation here to solve for the amount of solute. Because the amount of solute does not change when you dilute something. The concentration changes and the amount of solution changes because you've added more solvent. So if you think about some juice, you have some orange juice and you want to dilute it, you add more water, so the amount of water changes, the amount of the orange juice changes, the concentration of the juice changes, but the amount of the orange pulp and sugars and vitamins that were dissolved in the water has not changed because you haven't added any more of that orange, you've just added the water part. So that means that you are not changing the amount of solute, and the amount of solute before is equal to the amount of solute after. Then if we substitute in concentration times amount of solution for amount of solute, we're kind of substituting that because the amount of solute is the concentration times the amount of solution. Then we have that product is the same before and after. And that makes sense because if the concentration before is higher and the amount before is lower, then after you've diluted something, the concentration ends up lower, but the volume of what you have ends up higher. So a lot of people are very comfortable using this formula, this dilution equation. It's sometimes written with a C. It can also be written with an M because a lot of times we're dealing with concentration in molarity, and so the M makes that pretty obvious. So I have just a couple of these dilution style equations or dilution problems to work on. So it's a pretty straightforward formula. The only thing that needs to be done is to try to make a list and see which things you know and which things you are looking for. I think that's a helpful way to approach this. And it doesn't matter if you assign this first number, this first volume, to be V1 or to be V2. What matters is that you keep the volume that matches a particular concentration together. So we have 45.7 milliliters of this solution, the solution that's 3.50 molar. So we have to make sure that these are the same, that we assign these to the same situation. So 45.7 milliliters, if we make this V1, then the concentration 3.50 molar needs to be C1 because these two match. You can have them both match here, but they just both have to be on the same side and match. So our diluted solution has a volume of 300 milliliters, and that is the one that we don't know the concentration yet. So 300 milliliters matches the unknown concentration, 45.7 milliliters matches the 3.50 molar concentration. So here is the setup with the amounts plugged in. Then to get C2 alone, we just divide both sides by 300 milliliters. The milliliters are going to cancel, and so we end up with C2 being 0.533 molar. And that makes sense because it's a concentration, so it has the unit molar or mole per liter. It also makes sense that 0.533 is a lower number than what we started with. Because we did make it more dilute, that means the concentration should be going down. So sometimes it's helpful to make a little prediction like this. Okay, so first let's make a list of our variables. We want to make 450.0 milliliters, that's our volume that we want, and we want our concentration to be 0.500 molar of HCl. Then we have how many milliliters, an unknown volume, of a concentrated solution 5.75 molar. So we're going to start with an unknown amount of 5.75 molar, add some water, and then we will have 450.0 milliliters of 0.500 molar. So it makes sense that this volume that we start with is going to be less than 450 milliliters because we're going to dilute that up to 450 milliliters by adding water. So let's make a prediction that V2 should be smaller than 450 milliliters. And we can use this to double check our answer. If we come up with a volume that's a lot more than 450 milliliters, then we'll have to wonder how did we dilute that to only get 450 milliliters. So here is our setup with the numbers filled in. We can divide both sides by 5.75 molar. So that cancels everything on this side except for V2. It leaves V2 alone. It cancels the molarity on this side. So our units are going to be milliliters. And we end up with 39.1 milliliters as our volume. And this is smaller than 450 milliliters. So that did work out as predicted. So that can give us some more confidence in our answer.